Good afternoon, ladies and gentlemen. In this video, I want to go over the practice problem for practice C of chapter 13. And in this one, we're talking about convex mirrors. So it's in the other direction compared to a concave mirror. But before we read this problem, I want to draw your attention to the handout that I gave you that summarizes the properties of concave mirrors and convex mirrors on this lower part. So here's an example. The concave mirror, on this side, we see the focal point, and the C, the center, that's the radius. So the distance from C to the edge of your concave mirror is the radius, and half of the radius is the focal distance. All right, so here's our concave, and we're going to look at the difference of what happens to the image when it's a convex. The convex is in the other direction. Bottom line is this is the one you did for practice B, and for concave you have positive focal length. And if the object is on this side, which it is, then it's positive distance. And if the image is on the opposite side, then you have a negative distance. So P, the position, would be positive. And if your image is on the opposite side, it'd be negative. And if the image is on the same side, then Q would also be positive. Okay, so everything on this side is positive for concave, and the opposite side is negative. The convex, because it's in the opposite direction, where in the concave, the focal length, F, is positive, here, whatever they tell you the focal length is, you write down negative, and that immediately tells you that it's a convex mirror. And again, if the position's on the left side, then P would be positive, and if the image is on the right side, then Q would be negative. Okay, but the biggest difference is the concave, your F focal point is positive, and in convex, it's negative. So taking a look at concave mirrors, and I do hope you play with that link that I'm going to give you where you can play around and move the object and see where the image is. If you have your object between your, we can call this P, the point of the center of your lens, and the focal point, then the image is going to be behind the mirror on the other side, meaning Q would be negative. Okay, so you might want to write down that Q is negative. Negative Q. Okay, if it's exactly on the focal point, and guess what? Your position's at infinity. You're not going to see one. Okay, it's highly enlarged. And by the way, always have real and inverted. So your images are always going to be upside down. That's what inverted means. Okay. If your image is between C and F, anywhere between these two, then your image is beyond C. Okay, way back here, and it's going to be enlarged. Okay, so like your makeup mirror or your shaving mirror, etc. If it's exactly at C, if your image is exactly at C, then your object, if P is exactly at C, your position of your object, then your image is also at C, but it's inverted. And then if it's beyond C, way here, your object, then your image is going to be between C and F. All right. If your object is way super far away, then your image will be exactly at the focal point, okay, but really tiny. Okay, so moving on now to convex, you have less different options here, or less choices. What happens if your position is a specific distance between P and F? Okay, so your position is between P and F. So even though the focal point is here, the equal distance on this side, let's say F right here, if it's between the F and the P, then your image is going to be smaller, but it's going to be upright. Okay, and if you have it at infinity, it will be exactly at the focal point. All right, examples, side view mirrors of your cars. These are convex mirrors. And then maybe you've seen in the stores, those big, huge round mirrors on the corner at the inside of the store for security purposes. Okay, those are also going to be convex mirrors. So the image will be smaller, but they'll be able to see you still. And then, of course, ATMs, so that you can see who's behind you. If you haven't noticed, they're there. Okay, and let's see. I gave examples for the concave mirrors, solar heaters, astronomical telescopes, huge telescopes. Yeah, and like I said, the shaving mirror, the makeup mirror, and the headlights of the car, so you could see far. plus the deflectors on there. Okay, so now let's take a look here. This problem is a convex mirror with the radius of curvature 45 centimeters. Okay, so they tell you that the radius is 45 centimeters. Remember that the radius is like as if your curved mirror is a ball. The radius is this part, right? But we want the focal length, which is right in the middle. Focal length is exactly the middle. So the focal length must be half of 45. So 45 divided by 2, which is 22.5 centimeters. That's what they tell us. All right, now they tell you that it forms a 1.7 tall image. Look at that. They're giving you the image, not the object. Okay, and it's the height. So the height, we're going to say H prime for the height of the image is 1.70 centimeters. H is usually the height of the object. Height of object. All right. And they tell you that the image of this pencil is at a distance of 15.8 centimeters behind the mirror. Behind the mirror. Okay, so instead of concave, it's going to be convex. And I know that the image is behind the mirror over here. There's my pencil behind the mirror. Well, anything that's behind the mirror has got to be negative. So where P is for position, Q is the position of the object. So that'll be negative 15.8 centimeters. They want to know the object distance. Okay, so in this case, they want to know what is P. What exactly is P? All right, and they want to know if it's image, if the image, is it real or is it virtual? Remember, when you look at yourself in the mirror, that's a virtual image. So if I were to put a piece of paper there or something, I couldn't project that image onto anything. So that would be virtual. All right, and what is this magnification? Magnification. Hopefully you remember from the last, or in the book, it's negative Q over negative P. But it's also, the magnification is going to be H prime over H. So whatever the height is of the image divided by the height that you started with, that's the magnification. So maybe that'll make more sense to you. Whatever you end up with divided by whatever you started, that's the magnification. Just so happens that it's also negative Q over P. All right, and they want to know, is it inverted or upright? Is your image inverted or upright? And then I'm going to put here up or down. So did it stay in the same orientation or did it get flipped upside down? That's what the question is. All right, so there's what we're given. We're given the F and we're given the Q, and we want to know what the P is. And I highlight that because the same equation you had before is still true. 1 over the focal point, well, actually I like this way. I'm going to say 1 over P plus 1 over Q is equal to 1 over F. Okay, I like it that way because I'm going to solve for 1 over P. Okay, so I'm going to subtract 1 over Q to both sides. Subtract 1 over Q, subtract 1 over Q to both sides. And I end up with 1 over P. 1 over P is 1 over F minus 1 over Q. All right, so 1 over F they gave us, but it's a convex. It's convex. Because it's convex, then I know that the focal distance is less than 0. It's negative. So even though they gave us 22.5, we have to know, oh, this one's convex, so I got to make this negative. So this will be negative 1 over 22.5. Negative 1 over 22.5 minus Q, and they gave us Q as a well, they gave it to us as 15.8, but we know it's on the opposite side. It's back over here, so it's got to be negative. So I'm going to say minus a negative 1 over 15.8. Okay, minus a negative 15.8. All right, so I know that that's going to be a plus positive. So let's do that. 1 over P. Let's do that. Turn on my calculator. Okay, so I have a negative 22.5. Please invert that for me. There it is. And I'm going to add that to 15.8 inverted. Remember, that just means the reciprocal. Give me a 1 over that. And what do I get? I get 0.01. I get 0.01 0.0188466, etc. Okay, that's nice. That's 1 over p. I don't want 1 over p. I want p. So I'm just going to invert that. So p is equal to, let's invert that. Please give me the reciprocal. And I get this number. I have to press this. When that happens, you got to press this other button. Nice, they reduced it for you. All right, so I get 53.0597. So say about 53.1 centimeters. That's what P is equal to. All right, so now I know that even though this guy is about 15.8 centimeters here, then my object is way over on the other side at 53. Let's see, that's about 15. Well, it's not to scale. This one's over here. There it is. That one is at 53. Say at 53 centimeters over here on that side. All right. So we're not done yet. So we got the P. Now they want to know what the magnification is. Well, you got a couple choices here. I gave you a negative Q over P for magnification. There it is. Magnification. So let's do negative Q minus, but the Q is a negative 15.8. So negative 15.8 all over P. And we just figured out what P is, 53.1. 53.1. Okay, well, I'm just going to leave it in my calculator. So here's my little trick. I don't want to retype that. So I say, what's the inverse of that? And then I multiply that by 15.8. 15.8. Okay, I want to make sure. Am I recording this? Okay, I just want to make sure. All right, so there it is. We have our magnification is 0.29777, 0.2977, etc. Okay, there we go. So the magnification means it shrunk. So from my object, it shrunk about 30, down to 30% of its original size. Okay, 0.299778. All right, now they gave you what the height of this is. This guy here is 1.7 centimeters, and they want to know what this is. What's the height of that? Okay, so a couple ways you can look at that. We know that what you end up with over what you started is equal to the magnification. So we can start with that. What you end up with, what you started with, is 0.29778. And we end up with here 1.7. That's this one right here. So this one here is 1.7. 1.7 centimeters. That's that one. So I need to solve for h. So hopefully you can see I multiply h to both sides. I divide this to both sides. So I end up that h is equal to 1.7 divided by all this 0.29778, etc. All right, is it still there? Yes, it is. Okay, so it's in the denominator, so I'm going to flip it over again and multiply that by 1.7. And I get 5.7. 5.7 centimeters. So that's the height it started with. It started with about 5.7 centimeters, and then it shrunk, but notice how it stayed upright. It's still upright. So my answers then, it's not a real image. The image has got to be virtual because it ended up on the other side. And it is upright. So it is upright. Okay, it's upright. So what I'd like to do is show this to you graphically now. Show this to you graphically. So I took the time to draw it out, and then I'll review the problem again. So here's what I did. Here's my convex lens this time, and the focal point was 22.5. So I made each of these boxes 5. So 5, 10, 15, 22.5. So right here is the focal point. And then the image Q was at 15.8 centimeters. I put around 16 here. So there you go, 5, 10, 15, just to the right. So there is my image. So normally when you do these, you start with your object and then figure it out. But I just want to show you how the rays work. All right, so the first one. So by the way, I went ahead and just put this guy was at 53. We decided that it's 53. So I went out 10, 20, 30, 40, 50. The next one's 55. So this is my P, and here's my Q right there. Okay, so what do I do for my rays? See if I turn off this light, it's better. From the top, best as possible, you go straight to the convex lens and it is going to bounce off the reflection. But since this is a virtual image, you take that same ray through the focal point. I should have continued that. Should have continued it all the way so you could see it from here all the way through. So you can sort of see that line there. All right, so it goes straight, bounces off, but really you imagine it going through the focal point. That's one of them. The other one is the top of your image. No, I'm sorry, top of your object, not your image, and it goes straight through the center, straight to the center. So that's double the focal distance. Okay, so this is called the center, which I put R for radius, the radius there. All right, so that one goes straight through, and notice that those two lines intersect, and that's where my image is. Okay, and why? Because this ray would go straight here and bounce straight back because it's directed towards the center. And virtually, you can imagine it going inside the center, and that's where this is. And notice how the image, this one's the image is upright, just like the object. All right, so there's an example of how to do your ray diagrams with convex. So let's go through this problem again. They tell you it's a convex mirror, and they tell you the radius of curvature. So immediately I know what the focal distance is. I write down 45 centimeters and I divide by 2, and there's my focal distance. And this time they tell you that the image, this is the height. So I'm going to put H prime. That's my height of the image. And it says at a distance behind the mirror, So I immediately know that Q is negative. It means it's on the opposite side, the right side here. And it's 15.8. They want to know the distance for the object distance. So I want to know what P is for the pencil and its height. And they also want to know its height. Then they want to know if the image is real or virtual, what's the magnification, and if it's inverted or upright. So all we did was we start with your basic equation, basic mirror equation, which is 1 over P plus 1 over Q is equal to 1 over F. And this time I want to solve for 1 over P, or for P eventually. So I subtract 1 over Q to both sides. Got to keep remembering if it's convex, then the focal distance is negative. So I subtract a negative Q, because the Q is on the right side, so the Q is negative. So I have a minus, which is plus a positive. And there was my 1 over P. Then I flip it over, take the inverse, and I figured out what P was. So for your magnification, I could have just done Q over P. Well, I did. Here's my Q, negative. It's a minus here because the Q is negative. Divide that by the P. There's my magnification. So I go, oh, it shrunk. Okay, it shrunk. So that should tell you that if it started at 1.7, then it better be bigger, right? Because it shrunk when it went from the object, to the image. So always look and see if it makes sense. So you look at your magnification, and I need it to be bigger. That's another way to do it. I need to be bigger. So I divide it by 0.29778, whatever's in my calculator, and I end up with the height of the image, And since it was upright, I say it's upright, and it's on the other side, so it's a virtual image. And that's it. Make sure you play around with that website so you get a feel for how they change depending on where your object is and if it's a convex or a concave. All right, see you next time.